Hi, my name is Steffen Wiewel and I'll present to you our paper about latent space subdivision. I'll show you how to design a network with a modifiable latent space which allows for controllable and stable time prediction of fluid flows. The equations governing fluid flows are the Navier-Stokes equations, which are computationally expensive, where the cost grows drastically with increasing spatial resolution. Numerical simulations also face temporal constraints where instabilities can occur if the time step is chosen too large. Furthermore, modifying simulations externally, for example by adding an obstacle to the scene, is not straightforward to do. Usually the simulation needs to be rerun from the beginning. An interesting idea is to teach neural networks these complex dynamics, since they offer linear execution time and do not need handcrafted features such as regression forests. However, previous neural networks-based approaches led to instabilities over time due to the accumulation of error, which introduces a drift over prolonged time spans as seen in this demonstration. This video shows the movement of cold smoke in a cup predicted by a neural network. The example demonstrates the temporal instability introduced by networks without temporal constraints. We propose a neural network-based long-term prediction method with the advantage of being able to easily modify the latent space externally to meet the desired needs, such as boundary conditions. This is our method. As you can see, our neural network produces temporally stable, three-dimensional fluid flow predictions for 200 frames. Previous work applied a method called interval prediction to be able to arrive at such long time spans. When applying interval prediction, the neural network is predicting a few frames, then a classical Navier-Stokes solver is taking over and processes one step based on the predicted values. This keeps the prediction on track. With our method, solely the neural network advances the state of the simulation. We do not rely on a classical solver to compute intermediate steps. Morton et al. Proposed a method to use neural networks for the temporal prediction of computational fluid dynamic problems. Unfortunately, this method is strongly limited in flexibility and is only created for a single use case. Kim et al. Focuses on spatial compression and the properties of latent spaces. Their autoencoder with skip connections and their stream function-based loss to guarantee divergence freeness is a great base to start. Latent space physics focuses on a temporal prediction of fluid simulations and achieves good results but is limited by the need to use the pressure solver to arrive at long predictions. Latent space dynamics is a hot topic in deformable simulation as well, but shows only a modest speedup so far. Like previous work, we use neural networks to predict the motion of a fluid over time, but with the central goal to increase accuracy and robustness of long-term predictions. We propose to use a joint end-to-end training of both components, the fluid state compression and the temporal prediction of the motion. Such a joint training allows both components to build a holistic view of the underlying task, which is not the case for individual training. The joint training enables the network to propagate the error gradients from the spatial decoder through multiple recurrently connected temporal prediction blocks to the spatial encoder. Another key observation is the need to control the learned latent space, such that we can modify it during the simulation process to impose boundary condition and other known information external to the simulation state. Without such control capabilities, the underlying prediction model cannot react to external changes in the simulation domain. We therefore propose structuring the latent space through subdivisions, which separate the encoded quantities in the latent space domain. This enables us to directly manipulate the individual quantities in the encoded latent space domain and therefore, for example, feed back a density field that vectored externally with the predicted velocity field. The subdivision is enforced with a split latent space soft constraint for the input quantities velocity and density, and hence allows for alteration of the individual encoded components separately. This separation is a key component to robustly predict long-term sequences as demonstrated by our results. It enables us to precisely adjust parts of the latent space to adhere to physical behavior determined externally by well-understood classical methods. For the fluid state compression and the temporal prediction of the motion, we use two classical building blocks. The first one being an autoencoder that is a convolutional neural network that consists of several convolutional layers that allow for nonlinear domain compression, a very important property for our use case. A convolutional autoencoder compresses data from the input domain to a compressed representation called the latent space, which is usually much smaller than the input dimensionality. Afterwards, the latent space point is decompressed by the decoder. This leads to a reconstructed input that can be compared to the ground truth. The difference between the reconstruction and the ground truth is fed back through the network by backpropagation to adjust the weights in decoder and encoder accordingly. In the end, we arrive at a highly specialized latent space that achieves good compression for our trained task. The second building block are recurrent neural networks, or more specifically, long short-term memory cells, also called LSTMs. Those are able to propagate error through time, perfect for temporal predictions. Recurrent neural networks can be connected in many ways. The most common ones are one-to-one and many-to-many, but this is strongly task-dependent. In our case, we apply the many-to-one scheme. This means multiple input frames are handed over to our prediction network P. The prediction network internally iterates over those inputs and creates a temporal context. This context is then used to determine the next temporally consecutive output. More details can be found in the related work latent space physics. This is our proposed network structure. It consists of three parts, the first one being our autoencoder that contains an encoder and decoder block as described before. The autoencoder enforces spatial compression and yields our latent space domain C. The second part is the prediction loss. This includes our temporal prediction network that advances the state of the simulation in time by iteratively predicting the next time step based on the last predictions. The last part is our latent space split. This loss enforces the separation of input quantities, velocity and density in the latent space domain C. This feature provides the capability of exerting external control over the prediction. We now shortly discuss our loss functions. Our autoencoder encodes these two quantities, velocity and density, simultaneously as described before. The network was designed this way to benefit from synergistic effects that exist between those two quantities during the encode and decode step. The synergies exist due to buoyancy and boundary conditions that couple density and velocity. In our autoencoder loss, we use a sum of mean absolute as well as mean squared error of the respective quantities and the gradient of the velocity. The latent space split loss is performed twice, on the density and the velocity part. When the density is encoded, this loss forces the velocity part of the encoding to be zero. The same happens vice versa for the velocity component. This leads to an almost disentangled latent space domain, because the influence of the separated latent space entries can be clearly linked to the respective input quantities. This is shown with the green and blue dots in the schematic on the right. The no-split version is an example of a latent space of previous work. The mixed colors mean that the individual latent space entries have control over multiple input quantities. This makes a precise alteration impossible. The split schematic shows the result of our split loss, where we enforce a clear separation. This means we know which part of the latent space corresponds to which input quantity. With this knowledge, it is possible to exert precise control over the prediction in the latent space domain. Additionally, we include the supervised parameter loss proposed by Kim et al. As the last entry in our latent space. The prediction network performs a temporal transformation of its inputs to the temporal consecutive state. This means an input window of W states is transformed to the consecutive state as shown on the slide. The output of the last transformation is fed again into the prediction network to advance its own predictions forward in time. This means P is executed recurrently by reusing its own outputs as inputs for the next prediction step. The highlighted loss is a sum of autoencoder losses performed on the predicted latent spaces. This means the prediction error is evaluated in quantity space after decoding and is backpropagated through time and thereby through the whole network back to the encoder. We trained our network on several datasets in 2D and 3D to thoroughly evaluate the performance in different use case scenarios. Our dataset contain a variety of different smoke behaviors. We have hot rising smoke sources that move on the ground in random directions, and we also have sinking cold smoke that is contained inside a cup while the cup rotates and moves around, and thereby produces complex collisions with the cup obstacles. Those are examples for our moving smoke dataset. It contains a moving smoke inflow source that generates hot smoke continuously, which is rising and thereby producing complex swirls. This dataset contains 200 randomly generated scenes with 600 consecutive frames and exposes one control parameter in 2D, which is the movement on the x-axis, and two control parameters in 3D. The rotating and moving cup dataset contains simulations of cold smoke in a cup-shaped obstacle. The cup rotates randomly around a fixed axis and moves randomly on the x-axis. Similar to the moving smoke dataset, this one also contains 200 randomly generated scenes with 600 consecutive frames. We evaluated 3 networks trained with different loss functions. We are specifically interested in the stability of the latent space they generate for temporal sequences. For each of the plots, 200 frames of 20 different smoke simulations were encoded to the latent space domain with the corresponding autoencoder. The resulting latent space points were normalized with the respective maximum and afterwards transformed to 3 dimensions with PCA for display purposes. The first figure is generated with a classical autoencoder that was trained to only reproduce its inputs. This is similar to what happens in the paper latent space physics. For this classic autoencoder, no temporal constraints were imposed, and no supervised parameters were added to the latent space. The resulting PCA decomposition shows a very uneven distribution. Large distances between consecutive points exist in some situations, whereas in others, a large part of the samples are placed close together in a cluster. When adding the supervised parameter loss proposed by Kim et al. In the paper Deep Fluids, the trajectories become more ordered, but still exhibit a noticeably uneven distribution. This is shown in the second figure. Thus, a supervised parameter has a noticeable influence on the latent space construction. In the third figure, the results of the autoencoder trained with our proposed time-aware end-to-end training method are shown. This autoencoder applies the supervised parameter loss, as well as the direct loss on the output, and was trained in combination with the temporal prediction network P as described before. The visualization of the PCA decomposition shows that a strong temporal coherence of the consecutive data point emerges. This visualization indicates why our prediction network yield substantial improvements in terms of accuracy. The end-to-end training provides the autoencoder with gradients that guide it towards learning a latent space mapping that is suitable for temporal predictions. Intuitively, changes over time require relatively small and smooth updates, which results in visually more regular curves as shown in the rightmost figure. As described before, an important aspect of our method is to use the synergistic effects of the individual input quantities. We enforce the synergy effect by setting up our autoencoder to compress both quantities simultaneously with the same convolutional operations and weights. To evaluate this behavior, we created an encode-decode scheme that encodes the input and afterwards directly decodes the created latent space point. In this setup, we can now manipulate several parts of the process to directly see the influence on the output. For example, we can set the density part of the latent space to 0 to evaluate the impact the encoded density has on the reconstructed data. We observed that with input quantities set to 0, only average fields are obtained for both quantities. Removing the density information in the latent space, for example when Cden is set to 0, the reconstructed quantities are still similar to our full method but exhibit a decreased reconstruction quality. This indicates that the encoded density is not essential for a meaningful reconstruction, but certainly improves the quality when available. In the bottom row, second left, we see that without a meaningful encoded velocity, Cvel is set to 0, our reconstruction quality strongly deteriorates. This is plausible since without any velocity information, there is very little information about the state of the simulation. Furthermore, velocity encodes temporal behavior, which is crucial for reconstructing plausible fluid motions. In summary, we find that both density and velocity fields are reconstructed holistically. This means both quantities are reconstructed as a whole, are aligned and feature a similar reconstruction quality independent of which encoded quantity is set to 0. While our latent space is subdivided, both encoder and decoder provide a holistic view on the N and decoding process. However, the encoded velocity provides a larger amount of essential information, such that the decoder is able to reconstruct both quantities even when the encoded density is set to 0. We performed an ablation study on our method and will highlight the results shortly. This means we changed single parameters of our method and measured the resulting performance, as this indicates the importance of several aspects of the method. We use the peak signal to noise ratio as a metric. In general, this means the higher the PSNR value, the better the results. In our case, we calculated the PSNR of our predictions and the ground truth. In the first test, we measured the importance of the internal iterations of our prediction network during training. The more iterations were performed internally while training, the better the results in the end. The internal iteration count is strongly limited by the available GPU memory during training time. In the second test, we compared our latent space split loss to a simpler version. Both of the input quantities were encoded separately. Even though the simple split approach had more weight at its disposal, the performance was worse due to the missing synergy effect. In our third test, we altered the latent space dimensionality of our method. Unsurprisingly, the quality got better with a larger latent space. This parameter is again strongly constrained by the GPU memory at training time. Finally, we evaluated the performance of our method in terms of computation speed. We observed that our method scales better with increasing simulation complexity than a classical pressure solver. This led to a speedup of around ×9 in complex 3D scenes. In the following, we will see comparisons between simulations and predictions of our moving smoke scene. The no-split variant will be shown on the left, our proposed method in the center, and the ground truth on the right. In the previous examples, we have seen that our method stays close to the ground truth, whereas the no-split version is less detailed and at times deviates strongly. In the following, we will see comparisons between simulations and predictions of our rotating and moving cup scene. Our method clearly outperforms the no-split variant. Since our initial goal was to propose a method to enable long-term predictions, we also evaluated predictions ranging over a longer time horizon than before. In the following, we will see long-term rotating and moving cup predictions that span more than 400 frames. In the following, we demonstrate how the different methods react to a second inflow region that was not seen during training time. As seen in the examples, our method is capable of gracefully handling new inflow regions and positions unseen during training. To go even further, we added a solid obstacle to the moving smoke prediction. Note that obstacles inside the domain were so far only present in the rotating cup dataset. The moving smoke networks haven't seen an obstacle during training. You can see that our method reacts to the obstacle, whereas the no-split version ignores it completely. In the following, we will show some predictions of our 3D moving smoke scene. Enjoy! We have demonstrated an approach for subdividing latent spaces in a controlled manner to improve generalization and long-term stability of physics predictions. In combination with our time-aware end-to-end training that learns a reduced representation together with the temporal prediction, this makes it possible to predict sequences with several hundred rollout steps. In addition, our trained network can be evaluated very efficiently and yield significant speed-ups compared to traditional solvers. As future work, we believe it will be interesting to further extend the generalization capabilities of our network such that it can cover a wider range of physical behavior, In addition, it will be interesting to explore different architectures to reduce the hardware requirements for training large 3D models with our approach. See you on Tuesday in our Q&A session.